Hello students, Callie Daniels here. In this video, we're going to learn about the product rule and power rules for exponents. In example 1, let's write 4 times 4 times 4 in exponential form and evaluate it. Well, 4 times itself 3 times we can also write as 4 to the third power, where 4 is called the base and 3 is the exponent. Now as we evaluate this, we do want to go ahead and multiply 4 times itself 3 times, which gives 64. In example 2, we will identify the base and the exponent, then we'll evaluate. In part A, the base is -3. Notice that the negative symbol and the 3 are both in parentheses, and the exponent is 4. Now as far as evaluating this, we want to multiply -3 times itself 4 times. So this is going to give a positive result, isn't it? It's going to give us a positive 81. Notice the difference between part A and part B. Part B is the negative of 3 to the 4th. So in this case, the base is only that number 3. And so as we evaluate this, our negative sign is just going to hang out in front. And we want to multiply 3 times itself 4 times. That gives an 81 as we evaluate 3 to the 4th, but that negative symbol stays in front in this case. And be careful with that. So our product rule for exponents says that for any positive integers m and n, a to the m times a to the n is equal to a to the m plus n. In other words, we're going to keep the same base and add the exponents. For example, if we write 6 squared times 6 to the 5th, well, disregarding the product rule and just evaluating this as we did our previous examples, 6 squared is 6 times 6. And if we multiply that times 6 to the 5th, in other words, we put in 5 more of those 6's, we've got 1, 2, 3, 4, 5, 6, 7 in total. And we can also write that as 6 to the 7th. So the product rule for exponents gives us a shortcut. Okay, 2 plus 5 is 7, isn't it? In example 3, we're going to use the product rule for exponents to find each product if possible. Part A, -5 squared times -5 to the 4th, using the product rule, is -5 to the 2 plus 4, or 6th power. Evaluating this, and you can go ahead and use a basic calculator for this one. -5 times itself 6 times is a positive 15,625. In part B, y squared times y, which is y to the 1st, isn't it? Times y to the 5th. Okay, adding exponents, 2 plus 1 is 3, plus 5 is 8, and we can write that as y to the 8th power. In part C, 2x to the 3rd times 4x to the 7th. I'm going to rearrange some factors here and bring the 2 times 4 out to the front, times x to the 3rd times x to the 7th at the back. Well, 2 times 4 is 8, and x to the 3rd times x to the 7th, adding exponents, is x to the 10th. As we turn the page and look at part D, notice that in part D, those bases are different, aren't they? So our product rule does not apply here. Okay, but we can still evaluate this by evaluating each exponential involved. Okay, 2 to the 4th is 16, and 5 to the 3rd is 125, and 16 times 125 is 2,000. And again, you can use your basic calculator there if you'd like. In part E, here as well, the product rule does not apply because this is a sum and not a product. Now the bases are the same, okay, but we're adding terms here instead of multiplying them. We still can evaluate this by evaluating each term. 3 squared is 9, And 3 to the third is 27. 27 plus 9 is 36. Next, let's look at the power rule for exponents. For any positive integers m and n, a to the m raised to the nth power is a to the m times n. We raise a power to a power by multiplying the exponents. For example, 3 squared to the 4th power. Disregarding power rule A, we could still evaluate this. Okay, that 4 exponent says to multiply 3 squared times itself 4 times. Each of those 3 squareds is a 3 times 3. And altogether we have 3 to the 8th power. So the product rule, the power rule A gives us a shortcut, doesn't it? Jumping from this first step to the last, we could just say 2 times 4 is 8. So let's practice this power rule. In example 4, we're going to use power rule A for exponents and simplify. Well, power to a power multiply, and 7 times 5 is 35. So we can simplify this and write this as 4 to the 35th power. You don't have to evaluate that one. In part B, power to a power multiply, and 4 times 7 is 28. So we can write that as y to the 28th power. Next, we'll look at power rule B for exponents. For any positive integer m, a times b to the m power is a to the m times b to the m. In other words, we raise a product to a power by raising each factor to the power. For example, let's take a look at 2 times p to the 5th power. Well, disregarding this power rule B, we could still handle this. It's 2p times itself 5 times. We've got 5 of those in there. Then we can rearrange terms, can't we? Okay, or factors, I should say. We can bring those 2's to the front and leave the p's at the back. Okay, in other words, we've got the 2 as a factor 5 times and p as a factor 5 times, don't we? And that's essentially what this power rule indicates. Okay, we can just apply that exponent to both of those factors. Now let's practice this power rule. In example 5, use power rule B for exponents to simplify. Well, we're going to apply that exponent to each factor in here. So this becomes 3 to the 5th times a squared to the 5th times b to the 4th to the 5th power, right? So this is a 3 to the 5th power, or we might say 243. I'm going to go ahead and evaluate that because it was pretty easy to evaluate. A squared to the 5th power to a power multiply, and we'll write that as a to the 10th. B to the 4th to the 5th power to a power multiply, and we're going to write that as b to the 20th. So there's our simplified form. In part B, we've got negative 3m squared quantity to the 3rd. So we're going to apply that exponent to each factor. We're going to apply it to the negative 3. We're going to apply it to the m squared as well. Well, negative 3 times itself 3 times is negative 27. Oh, we need that 3 exponent up there, don't we? And m squared to the 3rd, power to a power multiply, gives m to the 6th. And that takes us to power rule C for exponents. For any positive integer m, this quotient a over b to the m is equal to a to the m over b to the m, as long as b isn't equal to 0. And all this says is as long as our denominator is not 0, because division by 0 is undefined. In other words, we raise a quotient to a power by raising both the numerator and denominator to the power. For example, if we have the fraction 5/3 squared, okay, disregarding this rule, we would know what to do, wouldn't we? That's 5/3 times 5/3. And we know to multiply in the numerator and multiply in the denominator. And if we convert that right back to exponential form, we would write this as 5 squared over 3 squared. And that's all that this power rule C is saying. You know, we can apply that exponent to both the numerator and the denominator. In example 6, we're going to use power rule C for exponents to simplify. And in part A, we've got p over q to the 5th, and don't make this too hard. That's p to the 5th over q to the 5th, applying that exponent to numerator and denominator. In part B, we see the fraction 1/4 to the 3rd. That's 1 to the 3rd over 4 to the 3rd, and I'm going to go ahead and evaluate this. 1 to the 3rd is 1, and 4 times itself 3 times is 64. So as we summarize our rules for exponents that we've learned thus far, for positive integers m and n, we have the product rule, which says when we multiply like bases, we add the exponents. For example, 6 squared times 6 to the 5th is equal to 6 to the 2 plus 5, or 6 to the 7th power. Power rule A to the m to the n, power to a power, multiply. For example, 3 squared to the 4th is equal to 3 to the 2 times 4, or 3 to the 8th. Power rule part B, if we've got a product raised to a power, just apply that power to each factor. For example, 2p to the 5th. Well, that's 2 to the 5th times p to the 5th. And lastly, in part C, if we've got a quotient or a fraction raised to a power, we can apply that exponent to both the numerator and denominator, as long as the denominator is not 0. For example, 5/3 squared is 5 squared over 3 squared. So now in example 7, we're going to just apply a combination of these rules to simplify. In part A, we've got 1/5 to the 4th power times 2x quantity squared. Well, 1/5 to the 4th is 1 to the 4th over 5 to the 4th. And 2x quantity squared, applying that exponent to each factor, is 2 squared times x squared. Well, 1 to the 4th is 1, and 5 to the 4th is 625. We're going to multiply this by a 2 squared, or 4, and x squared, and those are numerator values. So as a final answer, we'll just multiply it straight across on top and bottom. And let's write this as 4x squared over 625. And that's not going to reduce because 4 and 625 have no common factors. In part B, let's apply that outer exponent to each of these factors involved. So that's going to give 5 squared times k to the 3rd squared all over 3 squared. Well, 5 squared is 25. Power to a power multiply, so we're going to have a k to the 6th power, and in the denominator 3 squared is 9. Simplest form, 25k to the 6th over 9. And lastly here, part C, we're going to have a negative 3 to the 3rd times x to the 3rd times y to the 6th. I'm going to go ahead and multiply here, 2 times 3. This is all multiplication, so we're going to multiply that times x to the 8th, power to a power multiply, okay, and times a y to the 4th. Negative 3 cubed is negative 27. I'm going to use my product rule with x to the 3rd times x to the 8th Adding exponents, that gives x to the 11th. And similarly with our factors of y. Okay, 6 plus 4 is 10, so we've got a y to the 10th power. And last example here for these rules. In example 8, we want to find an expression that represents the area of the figure. And here we have a rectangle, don't we? We know that because of our right angle symbol. And the area of a rectangle is base times height. You might say length times width. Okay, true. Let's multiply those dimensions, okay? So our length, we've got here an 8x to the 4th. And our height is 4x squared. And we just simply want to multiply those, okay? Well, 8 times 4 is 32. And x to the 4th times x squared. Adding exponents is x to the 6th. So there's an example of an application of these rules. Okay. Good luck on those.